Hey everyone, and welcome to session 9 of High Performance LLMs from First Principles. So this week we're going to implement efficient inference. So kind of completing our arc there on efficient training and then efficient inference. Then I'm going to just talk a little bit about what else there is to learn. So right now we've talked a lot about performance, but what else is there in ML? As it turns out, there's a lot. And then if we have time, we'll deep dive into one more topic, which is numerics, which is one of the really interesting ideas and one place we can go deeper in ML. And then finally, this will be the second to last session, the last one I'll be teaching. But Sharad Vikram, the developer of Pallas, a kernel language for achieving high performance on TPUs and GPUs, will be joining us next week. And he'll be helping us showing us how to get high performance with Pallas. Very, very useful session. I hope folks are able to make the time to attend. So please, I know we have a small group today, but please just hop in with questions. I really helps me understand where folks are. So the first thing we're going to do is do high performance inference. So we're going to just do the generation step, and we're just going to do batch equals 1, but I think that'll be enough to teach us all the key things. So compared to where we were for inefficient inference, we have to do 2 real things. So we have to move away from, instead of passing in multiple tokens, we have to pass in a single token. And then after we do that, the neural net will actually be silly. And then to recover the good behavior, we're going to have to use the KV cache. So we're going to have to create a KV cache. And then we're going to have basically one token that will come through for the matmals. Then we'll use the KV cache. And that will be the entirety of our computation. So I think it will probably make more sense once I code it up. So let's switch to the VS Code and start programming. Perfect. So probably too small for folks. Is that reasonable?
I just see an infinity mirror.
Really?
Yeah, it's just showing your meeting.
Perfect. Let's try again. VS Code?
Yep, that works.
Cool,
Yes.
cool. Thanks for the help, folks. So what we're doing here is just running basically the code we had last time, doing inefficient inference. And what it's doing is our max sequence length is 128. So for each step, we pass in 128 tokens. We sample out one new token, and then we add that, and then we go again. So like to do these 30 steps that we've modeled out here, it doesn't take processing 30 tokens, it takes processing 30 times 128. So what we're going to do today, really the goal of today, is to process it in 30 tokens. Cool. So the steps, we're really just going to go around squashing bugs and seeing how things work out for us. So we're going to really just read the code from the top. Okay, RNG, whatever, our model seems good. Shaped and knit. So when we're doing this computation, we want to only process a single token. So that means that there's actually a different notion between our sequence length, which is the number of sequences we support, and when we run a forward step on the model, we want to process one token. So I'm going to make it be batch in sequences by 1. I think right now our batch in sequences is set to 1. So it's really 1, 1 there. Similarly, when we process our text, we want to process 1 token. Then we'll still do model.apply. We're going to have to obviously update model.apply to do the right thing. argmax still looks good to me. And then when we process tokens, the text, maybe this now this whole thing seems a little bit crazy. Maybe I'll just do it like this. So output string equals this.
Rocket,
and then we want
I don't see actually any changes happening.
Do other people not see other changes?
Yeah, it's static.
Really? When I go to the screen, everything works. But when I go to my VS Code screen, you can't see anything?
We see, but it's frozen.
Yeah, as you were toggling between the 2 screens, the VS Code updated, but it's still frozen. It's not updating real time.
Cool. Well, 3 times the charm. Thanks for the tip. And you see this. Is
Yep,
it up?
looks like it's updating.
Alrighty, perfect. So all I've been doing is going through and updating places where I had sequence length to be ones. So now we'll have output string, and our output is always the 0th token. So that's the token we're generating. So we actually, argmax now has to produce the next token. So this will be text. And then our output string will plus equals CHR. So turning our output into characters. And then text. I think we can do text 0, 0. I think that probably works. So now we've changed our inputs to be a single token. And the last thing we have to do is go through our code and think about which of this code will work in processing one token. So our embedding will work fine. We're embedding, and we'll get a batch by sequence by embed. But actually something that won't work will be this positional embedding. So here the way we're doing positional embedding is we're adding in something of 1 by sequence length by embed dimension. And if we add something, the way JAX and systems like it work, let's import NumPy. NumPy.ones, let's just like say 10, 10. And if we add that to something like a different shape, there's actually some fairly complicated rules for how NumPy and JAX will do broadcasting. So even though these arrays are different sizes, NumPy would like to add them, and you'll get something the size of this array. And then no, that doesn't depend on the order. So if we swap them, we'll get something out of size 10 by 10 either way. So these are called the broadcasting rules. They are actually worth learning, but we aren't going to cover them here. So our solution here is going to be called a dynamic slice. And we're going to do a few of these today. But with jax.lax, that dynamic slice and dem, okay, thank you, Jax, we'll take the positional embedding. Oh, perfect. So start index. So we need to know what position we are. So I'll make pause. We need to choose our slice size. So we always want a slice size of 1 because we're always processing 1 token at a time. And then our axis is always going to be 1. Perfect. And now we have this thing we need to, which is our pause, so our position, because each token now needs to know what position it is when it gets processed. So I'll add a position up there. And I will, now we have to just, as we evaluate things, add this. So it goes here. So it doesn't matter. We can just hit position. This one can be position. And then finally, when we call in here, we have to pass in a position. So if I haven't messed anything up too badly, what we're hoping to see is now the neural net should run, but it will actually produce garbage output. And the reason it will produce garbage output is because all of these feed forward layers are doing exactly the same. So like this operation is producing the right output when it multiplies a matrix by X. So is qproj and kproj, but attention, this implementation of attention assumes that we have access to all of Q, all of K, and all of V. So this is a pretty funny output. So that is actually going to be broken at this point. And it's just going to be broken because the Q, K, and V have shrunk in size. We don't have access to we have Q is the Q for a single tensor, and then K and V are also for a single tensor, as opposed to being for all preceding tokens. So we've kind of gotten to the point where the model isn't crashing, but it's not producing sensible outputs. So before we go any further, any questions about this? How are we doing? Are people processing where we are? Cool. It seems to be with us. KV cache. So the next step we have to do is to create the KV cache. So the KV cache needs to represent the keys and values we want to have for inference, and we're going to need to keep them up to date as we go. So we're going to create KV cache, and we're just going to output. Oh yeah, just speak up. No need to raise your hand. Victor,
No, sorry.
Anisha.
I think it got stuck again. The VS Code sharing.
Thank you for pointing that out. This is a sad technical series of snafus.
I'm wondering if it's related to like it being full screen or something.
Yeah, I mean, I usually do it full screen, but no
No,
doubt
then-
it is,
then
it
who
is
knows?
related.
It's working.
Perfect, thank you. So for ion layers, we have to say output. So we can do this however we want. I'm just choosing a key. There are actually many fancy schemes. So like max text, we use Flax to do this. But I think it might be just easier to see it explicitly. We're just going to initialize this thing. So JNP.zeros. And now we have to choose the right size. So it should be batch in sequences by the number of sequences, by the sequence length, so by sequence length, by num heads, and then head depth, num heads, head depth. Perfect. And then we will do the same for value. The value is actually shaped exactly the same way. Perfect. And then we'll just return it. And we can create this KV cache. And I guess just to look, there's nothing to the structure. I'll just put a breakpoint in, return output. Oh, interesting. I have my tab set wrong here. Cool. And we can just look at the structure, but all it's doing is initializing this as zeros. If I don't have any of this. And what we're going to do is feed the KV cache into each computation we do. And each KV cache entry will be written, will be consumed both as a reader and a writer in this computation. So I'm going to choose a random one, value 1. And we can see it's just a bunch of zeros. And if we look at its shape, 1, so batch, which is 1 here, there are 128. There has to be the capacity for 128 tokens. 4, which is the number of heads, and 128, which is the head dimension, how big each individual head is. So this is basically keeping track of the memory of the keys and values for the whole neural net. So now we want access to this in our model. So we'll just add it. By the way, I just changed screen, so let me know if I accidentally, so let me know if this screen share flakes out. So passing in the KV cache. And if we go up here, we'll pass in the KV cache. And now we have to figure out how we combine the Ks and Vs that we are computing in real time with the KV cache. So here there's I'm looking at my notes. So here there's a very similar thing we basically want to do. So we want to update the KV cache. So we're going to have to do two things. So one, write to the KV cache, then use that KV cache entry. So to write to the KV cache, it's going to be very, very similar to how we did before. So KV cache for key I. I think I is our iteration number here. Yep. Is going to be, and we're going to use a different JAX API. Dynamic, hopefully I'll get a prompt here. Dynamic update index and dimension, which is going to let us write into the KV cache. And we're going to want to write into PI. We're going to want to write in with K. And then we have to choose the sequence position. So that's going to be pause here. And then the axis we're writing on, which is 1. So this is basically taking our slice for a single sequence and writing it in. And remember, the sequence dimension is 1 in the position corresponding to this. So we're making a single write into the KV cache. And then now we want to actually use what used to be the KV cache as our K. So there's nothing shouldn't be any different from this. Then we will do the same for the V's. So we want this to be write to the value KV cache. We, of course, want to write with a value. And we want to use that value cache as our V. So one thing that's going to now show up if we print, let's say, q.shape, k.shape, and v.shape, is our q and k and v will end up having different sizes. So our q is a query just for this token, and our k and our v will be will represent all the history. It's the memory that the neural net has. And this is just implementing attention, token, causal attention, token by token. So we should see this print out. And then if we look at this carefully, not going great. So q.shape is, so let's just think this through. Q.shape here is 1 by 128 by 4 by 128. So that's carrying a sequence dimension. And then key and value are not carrying a sequence dimension. So that's interesting to see. One thing we should do is, interesting. Oh, interesting. So this is actually is correct here. Text. Let's print. So it looks like our shapes got messed up during the computation. So I'm just going to see what text.shape is. I think that probably we're getting that corrupted. I'm going to put it right here as well, just so we can think through this. Oh, probably actually the next thing we're going to do is going to fix that. Oh, interesting. Cool. Let's just see what's happening, what's going on the network first, and then we can think about how to fix it. Cool. So let's see what shape text ended up with. Okay, so that's one problem we have, is that text is coming out as a 1 by 128, and that's certainly not what we expected, right? So if we just remember what's supposed to happen here, is text is supposed to be on the scale of 1 by 1. So if we look at logits, they're coming out as 1 by 128 by 256, but they really should be 1 by 256 because it's batch is 1, sequence, we only want to process 1 token at a time by 256, which is our vocab size. So that does look like we have a bug here. I actually think that the next thing we have to fix anyway is the bug here. So I'm just going to fix it quickly, which is we haven't updated our attention. So we previously used attention ourselves, which was our own implementation of attention. We had a couple different implementations of attention when we worked on things, but here what we need is actually an attention that's able to work with different size Qs, Ks, and Vs. So I've made a very small change to our attentions in class, which I'm calling here attention with masking, which also just needs to know the position, and this is like directly out of our section on attention. So hopefully, if we call this and we pass in pause, that will be enough to fix this problem. We'll see. All right, perfect. So these sizes are starting to look like they make sense, right? Because this is batch sequence is 1 for Q, and then K and V are carrying the 128. So it does look like that probably solved the problem. Okay, so it's a very chatty print statement right now. Perfect. So we are now outputting the delightful output E. I actually noticed there's one more thing we should definitely be changing, which is we have to be returning the KV cache. So we have to make sure as we go, we output the KV cache. So let's do that. I actually don't know what else would be wrong here. So let's just do this. So we take the KV cache, we output the KV cache. And again, the idea here, and we should probably just put a breakpoint here, is we should see that we're writing to the KV cache as we go. So we can definitely take a look at that. So we can just interrupting the compiler. Hopefully we'll get through this time. So the idea when we inspect the KV cache is then we should see zeros in a lot of cells in the KV cache, but the cells with a sequence number small I or smaller should have non-zero entries. So if we grab the KV cache, it has a bunch of keys. So we can just take any of them. They should all have the same semantics. Key 0. And then so it's going to be batch by sequence by 4 by 128. And then it doesn't really matter. We can just take a whole slice through time to the sequence dimension. All right, so most of the cells are 0, which is what we expect. But the very first one is non-zero. And then if we continue this, we should see, well, now the first 2 are non-zero. And that should be true for every key. Right? We're writing from left to right in this KV cache. So we can just do this, and then boom, and we're just filling in the KV cache from left to right. And there's actually we're only showing the 0th number for the 0th head, but there's actually for this particular model 4 by 128, so about 512 numbers that are being written to for each layer of the neural net, and there are 8 layers, so about 4 kilobytes that we're using to represent state for each KV, so 8 total kilobytes for each number for each token. Cool. And now hopefully the model won't make sense, but hopefully now it'll start making roughly the same amount of sense our original model was making. Perfect. That is actually the original output, the company and the TTT. So the model never got super well trained, but it's working just how it was working before. But now we're processing 1 token at a time and using a KV cache. Before we go on, any questions here? Anything we should chat about? Cool. So we used to calculate a number of parameters. We used to calculate a number of flops. But instead of calculating a total number of parameters, let's calculate it as including the KV cache. So calculate number of parameters in the KV cache. Have a number, I don't know, call them floats. We can multiply by 4, so number bytes to read can be number floats times 4. So we're doing everything in float 32. So number of bytes to read, we can just print that. And we want to here basically model out how are we doing? And we can divide by 1E9. And we can get an answer in EB. So we might as well, I think we're done with actually using the model, so we might as well, we can just exit out here. And we can just, we've printed the number of bytes. We can import our timing utility. So it looks like we have that in timing util. So timing util dot simple time it. And we'd have to pass in our things. So here we have a model dot apply. So I'm just going to take this text up here, and let's just see how we're doing in timing. So if we jax.jit our model apply, we actually haven't jitted it yet. We can now run on state.param. So we have to pass in our arguments, text, I, KV cache. We have to give a task name. And then hopefully this will give us a time in milliseconds. And then if we should be able to print, definitely we can print our step time milliseconds. Perfect. And then we can print our memory bandwidth utilization in GB per second. And this is going to be our total bytes to read over 1E9, right, to get the gigabytes, divided by our step time milliseconds over 1,000. Cool. So for this platform, we know from kind of like prior experience that the peak memory bandwidth that's possible on the platform, the physical limit, is 1.23 terabytes, or 1,230 gigabytes per second. So we'd be really happy, like around half of that for something this simple. So we'll see how we do. Oh, looks like we're going to crash. Local variable I. Yeah, it does not matter. These are all invariant. The runtime will be invariant to I, so I'll set that to 0. So hopefully this will tell us our memory bandwidth utilization. Hopefully we'll get a reasonable number out. So the number of bytes this is telling us is 0.34. Our task took 1 milli. We print that out twice for whatever reason. And then we divide through, we get 305 megabytes. It's actually not very good. So 305 over 1230. So we're about 24.7%. This model is actually just so small that a couple of the things that happen in it are just different from what we're used to. So I'm just going to try again with a bigger model. So 2048, 8192, and we can go up to 8 heads. And then I played around with this a little bit before. Hopefully we'll get a sensible memory bandwidth for that. Cool. While we're waiting, any questions about inference? A lot's happened. So 616, so just about 50%. Yeah, get in there.
I have a question, kind of, I guess, about the KV cache. You see everywhere that it says attention is quadratic, and I think it is still quadratic with the KV cache. I thought flash attention is what can make linear growth with larger sequence length. Is that correct?
Yeah, so there's a lot of things going on there. First of all, great question. So during training, the number of flops in attention is quadratic, but flash attention lets the memory be linear. Separately, during inference, the size of the KV cache is growing linearly with the sequence length. But it's growing linearly with the sequence length, and you want to predict linear number of times, that's overall a quadratic, even though the KV cache is growing linearly. I hope that answers the question, Kellen. Great question.
Yeah, so flash attention, sorry, it can be used for training and inference?
So flash attention, the way it's normally used, the term is for training, and there's a related optimization called flash decoding, which is used during inference, which is a matter of semantics. But the same idea as in flash attention also helps during inference. If you it's like the rolling softmax trick.
Okay.
If you work it out, you'll see it also helps during inference.
Cool.
But it doesn't get around the fact that you need linearly more KV cache as you grow the size as a function of sequence length for normal methods.
And to go over that point, sorry, one more time for me. You mentioned that the KV cache grows linearly as you go through the sequence, but eventually it gets quadratic.
Well, what's going on is you have to do to predict n times. You need a KV cache of length n. So that's a quadratic, and how much memory you accessed, even though the KV cache itself is growing linearly. So the maximum memory you needed grew linearly, but the memory bandwidth grew quadratically.
Okay.
So it doesn't matter of what is the interesting thing in your system.
Okay. Thank you.
Great questions. Any more questions? Cool. So that was high performance inference. We got to 616 gigabytes per second, which is just a little bit over 50% memory bandwidth utilization. I'm sure we could do a bit better if we looked at some profiles, but still, I think a very reasonable number. There are some other optimizations that are relevant. So there's quantization, prefill. The prefill is like reading long prompts. Quantization we'll talk about a little bit today. And then batch greater than 1. So as we saw in a previous session, batch equals 1 can give you more throughput with the same memory demand. So it can give you a speed up, a perf TCO, perf per dollar benefit during inference. But I think that's kind of enough for inference. There were a couple things I wanted to cover. So first is we've covered a lot about performance in these sessions, and I do really love ML performance. And actually next week, Sharad Vikram, inventor of Palace, will be explaining Palace to us, which will help even go deeper into performance. But there's a lot more to ML than performance. So I do hope that you all continue to learn. So I think the other broad categories, speaking very, very crudely, is ML modeling, which is questions like how should we design the network? Kind of what type of layers should we use? What order, what mix, and what sizes? Like how should we quantize it? What data should we use? What optimizers? So many, many questions to go deeper. To very, very stylize the types of things that you answer in ML modeling. So you try different things, you see the loss, that's what we're trying to minimize during backpropagation. And here, this is a very, very typical graph. I just chose from a random paper. You can see our method, which is in red, does better than the other methods. And the idea is that this is a new innovation in ML modeling. And then the whole point is that you optimize these loss functions, and then the model can do interesting things. So this is the release for Gemini Ultra. And here it's comparing itself to GPT-4 and comparing how well it does on some downstream evaluation of how intelligent the model is. So just want to make sure people do not leave this with a one-sided notion of what ML is. Obviously, lots of performance is very, very important for ML, but the goal is to do well on downstream tasks. So with that spirit in mind, I just want to show you kind of like one whole fascinating world that we haven't had a chance to explore yet, but might be interesting to folks. So basically numerics. So this is one of the typical places where we need to think about both the performance of the system and the modeling accuracy. So basically, computer chips can do more math on lower bit representations of numbers. So if you represent a float with 16 bits instead of 32 bits, you do better. But the lower precision naturally introduces more error. So you have to make the right trade-off that makes the model work well. And it's actually quite subtle. Making that right choice, not so easy. So we're going to just show for a very, very simple example how precision plays out and what the right mix of compromises might be. Are folks able to see my screen? A1 and A2? Can folks confirm they can see?
Yes.
Perfect. So I'm just going to sum them. And I'm going to just point out a couple interesting things. So if we sum A1, we can actually do that twice even, because there's a lot of mysticism about floating point numbers. But one of the big things to know about them, so A1 is just like a vector basically of random numbers. And then for A2, I've done the same thing, but I shuffled it. So one of the first things we should notice here when we sum these is summing in the same order always should produce the same results, and summing in different orders will produce different results. So if we look at this sum A1, those are the same. And then sum A2, those are the same. But the sum of A1 and the sum of A2 is different. And because Python here is by default using really, really high quality floats, that's not different by very much. So you can see that even though because we use a different order, we got a different answer. The different answer is in the millionths, in the billionths place, or almost the trillionths place. So very, very small effects. But let's say we want to go to a finer resolution. We can start writing these sums ourselves, and this is what Jack is doing under the hood, and you can read it for yourself. jack sum, and we would call this F32. And we'll take input vec, and we'll write our accumulator. So our accumulator, let me just get my syntax right here. Our accumulator can be jacks.numpy.zeros. So we can just call it a 0, and jacks.numpy.dtype equals jacks.numpy.float32. Okay, so we have our accumulator. Excuse me, dtype. Perfect. Then for I in range len input vec. So now we can make whatever set of choices we want to. We can turn this into a jack type. So jacks.numpy.asArray input vec I. I guess we could just iterate over the numbers for x in input vec. We can turn this thing into an array, and then we can choose our dtype. So dtype equals jacks.numpy.float32. And we can add that into the accumulator. Beautiful. And then we should probably just make sure that they don't change the type on our accumulator for us. Equals jacks.numpy.asArray, and we can just cast the accumulator into its preferred type, which is dtype equals jacks.numpy.float32. So this is now we've written this thing where now we add the numbers as being float32s. We accumulate them into float32, and of course we will return accumulator, and we can now print jack sum F32 for A1 and A2. So this is A1 sum, A2 sum. This is jack sum. Excuse me. What is going on? So it's just showing us an empty array there. So this is none. Interesting.
I'm not.
Oh, sorry. Oh, sorry. What were you saying?
Never mind. You're good.
I think by saying 0, I was saying that my array had no size. So yeah, it won't work in PDB. I believe that I made my arrays have 0 size. What were you saying?
I was just checking simple stuff, just making sure the function was called, but I see it in the print.
Awesome. Well, thank you. So now we can see that we've gotten new numbers. And with this particular convention, we can see we get 19395 and 1394. So now we are starting to get more materially different answers, but they're still pretty close. And we can now ask ourselves, well, now we've used a lower decimal than Python seems to be using, but we can try going lower, and you can see what happens. So one thing you can do is you can cast the x's as we go into bfloat16. So this is now accum F32, input bf16, and we can write this one out, and then hopefully we should get some interesting we'll get gradually more interesting things as we take more as we use lower floating point numbers. So now jack sum, cool. And now we get 9409. And Actually, you see these two are very, very close because the additions happened in float 32, which, as we know, is pretty accurate. But they actually get a pretty significantly different answer from the right result. And that's because they've been cast into B float 16, which is introducing noise. But they always get the same result, regardless of the variance, because the float 32 is much higher precision. So if we want to see something that is going to behave pretty weirdly, is if we accumulate into B float 16. So when we add the two numbers, we cast them as B float 16. So there's a cum BF16, input BF16, and now this should be trouble. And the reason is because the BF16 is a pretty low precision number. I guess we can just comment out these prior because they're a little bit slow to compute. We can just comment those out. And what we expect to see is now we're going to get some much less good results. Okay, so now we just get total garbage as output. We know the right answer is 13939, but depending on the numerical order, your sum can either become 1.84 or 2.68. So that's saying that there's a lot, like the BF16 accumulating into BF16 is destroying our results here. And just to show one more quick case, we can do the opposite. We can cast each individual number into float 32, and then we can accumulate into B float 16. So this is input F32, accumulate BF16, and I think it's safe to say that's going to be trouble as well. And again, the reason is because all of our error is being introduced in the accumulator. The BF16 isn't fine-grained enough to accumulate. So when we do this, even though the inputs are so high precision, we're losing that precision in the accumulator. So this is not going to produce high quality results, and they're actually even lower quality than I expected, but still pretty interesting. Yeah, just speak up. Zach? Zach, your hands up? Okay, I'm going to assume Zach does not know his hands up. Cool. So that is kind of like a quick tour of like kind of a micro benchmark showing the trade-offs in using different floating point numbers. And then what I'm going to just quickly do is just like show kind of like what maybe the payoff is or something like that. So this is work actually I did with Matt, who's on the call, and some other folks, Lukash and Nietzsche. And here what we're doing is we're training an 8-bit. So we saw all those troubles in B float 16. So here we're training an 8-bit, and by that we mean we're multiplying an 8-bit using a scale factor, which is a slightly more advanced technique, and then accumulating in 16 or 32-bit, depending on some details. And we're able to show that our two loss curves for training in B float 16 versus training in int 8 are incredibly, incredibly similar. And you can even zoom in, and you can just see how similar they are here. So this is usually, we nowadays do int 8 on TPUs and FP8 on GPUs. But really 8-bit is quite common. And then you might get like something like a 50% training speed up with this really, really small gap in quality. So numerics, super, super important. And also, as we were seeing, a very deep field. So understanding, they bridge performance. You want to find numerical recipes that are performant, so things run fast and converge well. So there's a very small gap in quality. Slava, I think you're on mute.
Yes, I was right. So if training in int 8 is so much faster than training in bfloat 16, right? Why doesn't everybody use it? What's the catch? Why didn't entire industry switch to 8 bits by now in training?
Well, the industry is switched to 8 bits. It's just 8 bits on floating point 8 on H100. So it's a good question, but it's not. It's not a counterfactual. The largest companies are doing that. Great question, though. So like our ML perf results, we do in int 8. NVIDIA does them in FP8. Yeah, NVIDIA is going smaller on their new floating point numbers. So huge success at 8-bit for training and then also for inference. Cool. And that's all I had here. So last session will be next week, a Palace deep dive with Sharad, which is actually very, very delightful. He's done it for me before. Highly encourage folks to join. Palace is super, super important on both TPUs and GPUs if you're programming in JAX. Okay, well, any last questions?
Other than the accumulator, are there other parts of the network that's particularly sensitive to numerics?
Yeah, so that's a really good point. So within attention, the QK which outputs W, and WV projections multiplies within attention are both typically not done with 8-bit, either for the TPUs or GPUs, or either in 8 or FP8. And the reason for that is actually a hybrid reason. That it hurts convergence and it doesn't give any speed up because you're under so much of the VPU pressure. So it's not enough MXU for you to actually get a big speed up there. So that's the next most sensitive point. And then actually also the embedding. So the output of embedding to get to the logits, also fairly numerically sensitive.
All right, thanks.
Good questions. Zach, my question is, how do you have a different, how much precision is important? Or some examples where it is important and some where it might not be. Yeah, so again, nothing beats doing the ablations carefully. So I think BF16 for your map moles is now totally standard. I think that's safe. But anything past that, if you really want to do ablations, as you're quantizing things, see the impact on loss, and then quantize iteratively. The safest things, as we were just talking about, are quantizing with the transformers, where I have the most experience, is quantizing the feed forward, the QKV proj, and the O proj, and then everything else is a little bit riskier. Great questions. Any more questions?
I had one quick kind of tangential question. Where would you suggest to start to explore the idea of like model evaluation for something that's been fine-tuned or trained for a specific space, instead of just these standard benchmarks? Because I know those exist for general LLMs, but what if you want something context specific? Do you know if there's any development in that space?
I mean, there's a lot of development. So teams all have their own benchmarks, and they
Okay.
come up with their own ways of evaluating the models, and then as they make changes, they're evaluating
Okay.
on that axis.
And is drift something that should be worried about? Like, I've read about it some. What is kind of the time scale you could expect to drift typically?
Yeah, so drift, I think, is like a little bit of a romantic notion, but what people mean by that is that the inputs are changing over time. So you deploy some neural net, and like on the day you deploy the neural net, people are asking about the weather in like Vancouver, and then you get customers in Florida, and their questions end up being very, very different. So the rate at which you expect drift really depends on your application. And
Okay.
depends on how people are changing in the way they use your application.
Okay. Cool.
So yeah, it's hard to answer.
Sure.
But it's a good question. Zach asks, slight follow-up, do you have any thoughts on 1.5-bit LLMs? So there was a very interesting paper recently, 1.58-bit LLMs, which Zach is probably referencing as well, which was showing multiplication in 2 bits. So this is something where probably I can't go into too much detail. But let's say that maybe the zooming out, there's a trade-off between, as we lower the quality of the numerics, we are putting more pressure on row and column and sub-row and sub-column scaling, versus the MXU. So we put more pressure on the vector processing unit and less on the matrix multiply unit. And then the question is, like, where is the right end game? And what's the balance there? And I have to admit, I do not know the answer to that question, but I do think we see hardware clearly evolving toward more VPU pressure, less MXU, smaller MXUs, and so far it's always been the right call. So very, very excited, and very, very excited about the new generation of NVIDIA hardware. which will have FT4, so 4-bit floating point numbers, which should be very, very interesting to play with. Great question. Any more questions? Awesome. We'll see everyone next week for the Palace Deep Dive with Gerard. It's going to be a lot of fun. I've received it before. It's real good. Bye, everyone.